Okay, so are you ready for this one? I think this might actually break your brain.
Oh, yeah. Hit me.
All right, so you sent us these excerpts,
Rem-
yeah, from pasted text, and then this like theoretical paper that's based on this trilogy of books called Gravity and Creation by L.S. Larkey.
Oh, wow.
And let me tell you,
Oh,
this is
right.
wild.
Lay it on me.
It's called the Grand Fibonacci SMF RVS Theory of Gravity. I was just going to call it GF for short.
Okay.
GF for short.
Yeah.
And basically what it does is it completely flips the script on gravity.
Okay, so instead of this massive force pulling everything together,
Right.
Larky's proposing that it's actually a push
Whoa.
generated by the interplay of two fields.
Okay, I am already so intrigued.
Yeah.
But I got to be honest,
Sure.
my physics is a little rusty.
Okay.
So break it down for me. Like, what are these fields and how do they create this push
Right.
that we feel as gravity?
So think of it like this. Imagine the vacuum of space.
Okay.
It isn't just emptiness. It's more like a giant 3D map where every point has a different value representing the pressure there.
Okay.
That's what Larkey calls the relative vacuum of space, or RVS.
RVS.
Now add another layer to this map,
Okay.
something called subtle magnetic fields, or SMF.
SMF, got it.
These fields influence how the vacuum pressure, the RVS, behaves.
So instead of like a planet's mass pulling everything towards its center,
Right.
it's like the vacuum is pushing things outwards.
Exactly.
That's crazy.
And because both of these fields are dynamic and constantly interacting,
Right.
they create this push and pull effect that we experience as gravity.
So if I'm understanding this correctly, it's kind of like blowing up a balloon.
Uh-huh.
The more air you blow in, the higher the pressure inside, and that pressure pushes the rubber outwards.
Yeah.
So in this theory, the vacuum of space is kind of like the air in the balloon
Mhm.
constantly pushing outwards.
That's a great analogy.
Okay.
Now take that concept and apply it to a forming planet. As the planet gathers matter, the SMF and RVS interact in a way that actually creates negative vacuum pressure inside.
Negative vacuum. Okay, my brain officially needs a reboot.
I know.
How can something be less than empty?
It's a bit mind-bending, I know.
Yeah.
Essentially, the vacuum pressure inside becomes so strong that it repels matter from the center outward.
Okay.
It's like the vacuum itself is pushing everything away from the center,
Whoa.
creating a hollow shell.
Wait, hold on. So you're saying that Earth is hollow?
Yeah.
I thought we debunked that ages ago.
Right.
What about like volcanic eruptions and tectonic plates shifting?
Mm-hmm.
Doesn't that suggest a molten interior?
Those are great questions, and they highlight how this theory challenges our conventional understanding of geology.
Okay.
Think about the way we study Earth's interior using seismic waves.
Okay.
Those waves bounce around,
Right.
and we interpret those bounces as evidence of different layers and densities.
Okay.
But what if those waves are actually interacting with the boundaries created by this negative vacuum?
So it's not that the data is wrong.
Right.
It's our interpretation of it that might be off.
Exactly.
Right.
Larkey suggests that what we perceive as a dense core could actually be the signature of this intense vacuum pressure pushing outwards.
Wow. Okay.
And that brings us to one of the most mind-boggling aspects of this theory.
Okay. Fibonacci scaling.
Fibonacci scaling, is that like some kind of cosmic zoom function?
You got it.
Okay.
The theory states that the same rules of push and pull,
Okay.
the same interaction between SMF and RVS apply at every scale in the universe,
Yeah.
from tiny asteroids to giant stars.
So if Earth is hollow, does that mean everything else is hollow too?
According to Larkey, yes.
The moon, Mars, even the sun.
It's this idea of a shell-laminated universe.
What?
Every celestial body would have this hollow structure created by the interplay of SMF and RVS.
Okay, I'm trying to wrap my head around this, but if the sun is hollow, where is all that energy coming from?
Right.
What's powering the sun if there's no dense core fusing hydrogen into helium? This is where things get really wild.
Okay.
Larkey proposes that the sun's energy actually comes from the intense interplay of SMF and RVS within its boundary layers.
Okay.
This creates the plasma phenomena we observe.
So instead of a nuclear furnace at the core,
Right.
it's more like the sun's outer layers are generating all the heat and light
Mm-hmm.
through some sort of cosmic friction.
It certainly is.
That's crazy.
And it raises so many fascinating questions about how stars form, evolve, and eventually die.
This is a lot to take in.
Yeah.
So we've got hollow planets, a hollow sun. Where do we go from here?
Right.
What other implications does this theory have for our understanding of the universe?
Well, remember that Fibonacci scaling we talked about?
Yeah.
If this push-based gravity works the same way at all scales, then it should apply to galaxies too.
Hold on. Are you suggesting that this theory could explain how galaxies rotate
Exactly.
without needing dark matter?
But before we get into that, let's take a moment to make sure we're clear on how these fields actually work.
Yeah.
We've tossed around SMF and RVS a lot.
Right.
But how are they actually defined in this theory?
Yeah, I'm still a little fuzzy on that.
Sure.
What exactly are these subtle magnetic fields, and how do they interact with the vacuum?
Great question.
Yeah.
Larkey describes the SMF as a vector field.
Okay.
Think of it like a map of forces,
Okay.
where each point in space has both a strength and a direction associated with it.
So it's not just that the SMF exists.
Right.
Its influence changes depending on where you are in the universe.
Precisely.
Okay.
And it's not static either.
Okay.
It's constantly evolving and responding to changes in the RVS,
Right.
the vacuum pressure around it.
Okay, so the SMS is like this dynamic web of forces spanning the universe. What about the RVS? How does Larkey define that?
The RVS, as we discussed earlier, is a scalar field, which is basically a value that varies from point to point,
Okay.
representing the vacuum pressure or density at that location. Imagine it as a constantly shifting landscape of pressure, kind of like a cosmic weather map.
Okay.
But instead of tracking temperature or wind,
Yeah.
it's tracking the pushiness of the vacuum.
So areas with higher RVS values would have a stronger outward push.
Exactly.
Got it.
And the scalar field is also dynamic,
Right.
changing over time,
Okay.
and influenced by the SMF and other cosmic conditions.
Wow. This is really making me rethink how I visualize space.
Yeah.
Not just emptiness,
Yeah.
but this dynamic field of energy and pressure constantly pushing and pulling.
And remember, it's the interaction,
Right.
the coupling of these two fields that Larkey believes creates the force we perceive as gravity.
Okay.
It's a cosmic dance of push and pull,
Wow.
constantly shaping the universe.
Oh, okay.
But how does that dance play out on the scale of galaxies?
All right, let's get back to that.
Okay.
You mentioned that this theory could explain galaxy rotation without dark matter.
Right.
I'm skeptical, but very curious to hear how that works.
It's definitely a bold claim. Let's dive into it.
Okay, so how does this push-based gravity explain those crazy fast galaxy rotations
Right.
without needing dark matter?
So you've probably heard that galaxies spin way faster than they should,
Right.
based on like how much visible matter we can see.
No, that's the whole dark matter thing.
Exactly.
It's this invisible scaffolding holding galaxies together.
Yeah.
Because gravity alone isn't strong enough to do it.
Mm.
Honestly, it's always seemed like a bit of a cheat code to me.
Yeah, I think a lot of people share that skepticism. You know, the current model says we need this huge amount of dark matter
Right.
to account for that extra gravity. But
Yeah.
Larkey's proposing that instead of adding invisible matter,
Okay.
the answer lies in the SMF and RVS.
So instead of adding invisible matter, we just need to tweak our understanding of how the vacuum itself behaves.
Precisely.
Okay.
Think about it.
Yeah.
The vacuum pressure, the RVS,
Right.
isn't uniform.
Sure.
It varies throughout space.
Right.
Now imagine those subtle magnetic fields, the SMF interacting with these variations in vacuum pressure
Okay.
at galactic scales.
Right.
This interaction could create additional outward push, especially in the outer regions of galaxies.
So the same force that creates a hollow planet could also be giving galaxies an extra spin
Yeah.
without needing dark matter.
Mm-hmm.
I mean, I'm starting to see how this all ties together.
Yeah.
But are there any specific observations that support this idea?
That's the exciting part.
Okay.
Larkey's model can actually replicate the observed rotation curves of galaxies without needing dark matter.
Wow.
By adjusting the equations for how SMF and RVS interact at those massive scales,
Right.
the theory predicts that extra push that we observe.
Wow, that's pretty compelling. So
Yeah.
instead of invoking this mysterious dark matter,
Right.
we just need to understand how the vacuum itself behaves.
Mm-hmm.
That's elegant.
It is.
But does this push-based gravity only work for galaxies?
Right.
What about the expansion of the universe? Isn't dark energy supposed to be the driving force behind that?
Ah, another great question. You're right. The current understanding is that the universe is accelerating. Expansion is driven by this mysterious dark energy.
Right.
But just like with the galaxy rotation.
Let me guess, it all comes back to those SMF and RVS interactions.
You got it.
Okay.
Larkey suggests that the expansion of the universe isn't driven by dark energy,
Okay.
but rather by the changing dynamics of the SMF and RVS over cosmic time.
Okay, so help me visualize this. So
Sure.
instead of dark energy pushing everything apart, We have this changing vacuum pressure.
Exactly.
It's doing the heavy lifting.
Imagine it like a cosmic pressure cooker.
Okay.
As the universe evolves, the interactions between the SMF and RVS change,
Right.
causing the overall vacuum pressure to shift.
Right.
And that shift is what drives the expansion we observe.
Okay.
And the best part, Larkey can actually adjust the equations to match the observed expansion without needing to invoke any dark energy.
So this one theory, based on this push and pull relationship between the SMF and RVS, could potentially explain both galaxy rotation and the expansion of the universe. That's incredible.
It really is.
It's like unifying these massive cosmic phenomena under one elegant framework. But I have to ask, how does this theory deal with things like black holes?
Right.
Aren't those supposed to be these like incredibly dense points?
Yeah.
Where gravity is so strong that nothing can escape?
Black holes are definitely one of the most extreme environments in the universe.
Yeah.
But Larkey's theory has an answer for them, too.
Okay.
It all comes down to the concept of negative vacuum saturation.
Okay, remind me what that is again. We touched on it earlier.
Yeah.
But it's such a strange concept.
Essentially, it means there's a limit to how tightly the vacuum can be squeezed.
Okay.
How negative the pressure can get at a certain point.
Right.
It reaches a saturation point.
Okay.
And pushes back, preventing the formation of a singularity.
Right. So even black holes wouldn't have infinite density.
Right.
There would be a point where the vacuum pressure just says, nope, no further.
Exactly.
Right.
In this framework, even black holes would have a finite, albeit incredibly dense core.
Okay.
They wouldn't be these bottomless pits
Right.
of infinite gravity that defy the laws of physics.
That's reassuring in a weird way.
I know.
So this theory says that even the most extreme objects in the universe still obey the rules of this push-based gravity.
Right.
But how does this theory handle those ripples in space-time?
Right.
Those gravitational waves that were predicted by Einstein's theory and have actually been observed.
Yes, gravitational waves. That was a huge confirmation of Einstein's general relativity.
Yeah.
And you might be surprised to hear that Larkey's theory can accommodate them as well.
Really? But how can waves travel through a vacuum that's already pushing things around?
Right.
Seems like those waves would just get lost in all the commotion.
It's a bit counterintuitive.
Yeah.
But remember how we talked about the RVS being a dynamic scalar field?
Right.
It's not just sitting there. It's constantly fluctuating and responding to changes in the SMF and other cosmic events.
Right. So the vacuum itself is already in motion.
Exactly.
It's this ever-changing landscape of pressure.
Now imagine two massive objects, like black holes, orbiting each other.
Yeah.
Their movement creates disturbances in both the SMF and the RVS.
So their movement creates ripples through the vacuum.
Yeah.
Kind of like a boat creating waves in a pond.
That's a great analogy.
Okay.
But instead of waves in water, these are waves in the vacuum pressure itself.
Okay.
And they propagate outwards at the speed of light.
So those are what we detect as gravitational waves.
Right.
But how can Larkey's theory match the predictions of Einstein's general relativity?
Yeah.
Which is based on the curvature of space-time. Those are pretty different ideas.
That's the beauty of it. Even though Larkey's theory has a completely different starting point.
Yeah.
A push-based gravity instead of a pull-based one.
Right.
The math ends up producing remarkably similar predictions.
Wait, so two completely different theories can arrive at the same observable outcome. That's incredible.
It really is. It speaks to the power of mathematics to describe the universe in different ways.
Yeah.
And it's a testament to Larkey's work.
Yeah.
That their framework can accurately model gravitational waves.
Right.
Even though it's based on such a different understanding of gravity.
So we've got planets, stars, galaxies, black holes.
Right.
Even gravitational waves. All fitting into this push-based universe.
Yeah.
It's truly mind-boggling.
It is.
But if this theory is so comprehensive, why haven't I heard of it before? Why isn't everyone talking about hollow planets and the grand Fibonacci theory?
That's the challenge with any revolutionary idea, especially one that challenges our fundamental understanding of the universe.
Right.
It takes time for new concepts to be scrutinized, tested, and ultimately accepted by the scientific community.
So it's not just about whether a theory is right or wrong. It's about whether it can stand up to the rigorous process of scientific inquiry.
Precisely. The grand Fibonacci theory, while incredibly intriguing and potentially groundbreaking, is still relatively new.
Right.
It needs to be poked and prodded, challenged, and refined.
Yeah.
And that brings us to the question of
Yeah.
what kind of evidence could really make or break this theory?
Yes. Let's talk about that.
Okay.
We've explored the theory itself.
Yeah.
But how do we actually test it?
Right.
What are the next steps in figuring out if this push-based universe is actually the reality we live in?
There are a few key areas where further research could really shed light on the validity of this framework. One area is in more detailed analysis of gravitational waves.
Okay, so we talked about how the theory can replicate
Right.
the basic patterns we've observed. But is there something specific about gravitational waves
Yeah.
that could distinguish between Larkey's theory and general relativity?
That's a great question. As our gravitational wave detectors become even more sensitive,
Okay.
we might be able to detect subtle differences in the waveforms.
Okay.
Tiny deviations that could point to a push-based origin rather than the curvature of space-time.
So it's like looking for the unique fingerprint of the vacuum,
Exactly.
the subtle signature of these SMF and RVS interactions
Right.
playing out on a cosmic scale.
If we could detect those subtle deviations, it would be a huge step
Yeah.
towards confirming that gravity might actually be a push rather than a pull.
That'd be huge.
It would.
Yeah.
Another area where the theory could be tested
Okay.
is in cosmology,
Okay.
specifically in our understanding of the large-scale structure of the universe.
Okay, so we talked about how this push-based gravity
Right.
could explain galaxy rotation and the expansion of the universe.
Uh-huh.
But are there other specific predictions
Absolutely.
that could be tested observationally?
The way galaxies cluster together,
Okay.
the intricate web of cosmic filaments and voids,
Right.
all of this is influenced by gravity.
Yeah.
If the grand Fibonacci theory is correct,
Yeah.
it should be able to make precise predictions about these structures.
Okay.
Predictions that could differ from the standard model of cosmology.
So we could compare the cosmic web predicted by this theory to
Sure.
the actual distribution of galaxies and clusters that we observe.
And if the theory's predictions match the observations more closely than the standard model,
Yeah.
that would be a strong indication that we're on the right track.
Okay. Gravitational waves and the large-scale structure of the universe. Those are some pretty big picture tests.
They are.
Are there any other ways we could look for evidence?
There is one more, and it's incredibly ambitious.
Okay.
We could try to directly detect the SMF and RVS themselves.
Wait, seriously? But those are such subtle fields.
I know.
How could we possibly measure them directly?
It would definitely be a monumental challenge.
Yeah.
But as technology advances, who knows what might become possible?
Right.
Maybe we could develop instruments sensitive enough
Okay.
to measure those minute fluctuations in vacuum pressure.
Right.
Or detect the influence of those higher dimensional magnetic fields.
No, that would be a discovery for the ages.
It would.
Definitive proof that the universe isn't just pulling us together,
Right.
but pushing us outward as well.
Imagine the implications
Wow.
for our understanding of gravity,
Yeah.
the nature of space and time, and
Yeah.
even the very fabric of reality.
Yeah.
It would be a paradigm shift of epic proportions.
Wow. I'm speechless. This deep dive has taken us from the depths of hollow Earth
Right.
to the farthest reaches of a potentially hollow universe, all driven by this push-based gravity and the intricate dance of these two fields, the SMF and RVS.
It's a lot to think about.
It's incredible to think about. I mean, it really is mind-boggling, isn't it?
It is.
And, you know, even if it turns out that not everything is hollow,
Right.
just like exploring this theory has really challenged, like, my assumptions about how the universe works.
That's the beauty of scientific inquiry, isn't it? It's
Yeah.
not always about finding definitive answers,
Right.
but about asking the right questions.
Yeah.
And being open to new possibilities, even if they seem outlandish at first.
Absolutely. And I have to admit, the idea of a universe driven by push
Yeah.
instead of pull is strangely liberating. It's like a whole new perspective on reality.
It makes you wonder what other fundamental assumptions we might be clinging to
Right.
that could be overturned by a new way of looking at the universe.
Well, I think this deep dive has shown that
Yeah.
even the most established scientific theories are always open to revision, as new evidence emerges and new ways of thinking challenge the status quo.
Precisely, science is a constantly evolving process, and that's what makes it so exciting.
Right.
There's always more to learn,
Yeah.
more to explore, and more mysteries to unravel.
And sometimes the most radical ideas, the ones that seem the craziest at first,
Right.
can lead to the most profound insights.
Exactly. And who knows, maybe someday, instead of just landing on Mars,
Yeah.
we'll be venturing into its vast, hollow interior.
Right.
If Larkey is right.
Now, that's a deep dive I would sign up for.
Yeah.
It makes you wonder what other secrets the
No.
cosmos is hiding, just waiting to be discovered.
Absolutely it does. So to everyone listening,
Yeah.
keep questioning.
Yeah.
Keep exploring and keep embracing the infinite possibilities of the universe.
And if this deep dive into L.S. Larkey's Grand Fibonacci SMF RVS theory of gravity has sparked your curiosity,
Yeah.
sure to check out their Gravity and Creation trilogy and explore this wild world of hollow planets, a plasma boundary sun, and a universe driven by push, not pull.
Until next time, keep looking up and never stop asking, what if?
This is The Deep Dive signing off.
It's